Welcome back, everybody. This is Mr. Wakefield, and we're looking at section 3.5 right now. And I just want to let you know right off the top that this is one of the tougher sections. Okay, this is one of the longer sections. All right. It doesn't mean that each step is necessarily difficult, but there's just a lot of stuff in each one of these problems here. A lot of steps to learn and to get better at. All right, but like any problem, the more you practice it, it's going to get easier, and it's not going to seem so overwhelming after a while. All right, but this is definitely one of those types of sections where the problems are a little bit long. Okay, here's what we're going to be doing. Let me just look at some of the problems, give you a visual of what we're looking at here. If you look at the first couple problems along with the ones after that, you'll see that the function is equal to a fraction. All right, that's why they call it a rational function. Usually the word rational is a reference to a fraction. All right, but when you do graph a function that's equal to a fraction that has a polynomial on the top and bottom, which is what a rational function is, it is different than the last section where we just had the polynomial equal to just, the function was equal to just a polynomial right there. It wasn't a fraction. All right. The steps here are completely different, even though we're still graphing. Okay. So, and again, function f of x equal to a fraction with a polynomial on the top and bottom. What you do is a six-step process, okay? And it mentions these 6 steps, at least it starts them here on the front side of the worksheet. Okay, we'll go through those. Each step is involved, okay? A lot of stuff going on, so we'll be careful about it, all right? And we'll get through this slowly but surely, all right? So let's go ahead and just jump right into it, and then we'll look at each piece of detail one thing at a time here as we go along. All right, so the first step in all of these problems is make sure the fraction's in lowest terms. Okay, the function is equal to a fraction, so the fraction needs to be in lowest terms. If it is, then you can jump right to step 2. All right, let's take a look at this first problem here. As we reviewed back in the as it was reviewed back in the prerequisite review packet, how do you get a fraction in lowest terms when there's got variables and multiple terms and stuff? All right, you factor everything. You identify your factors. If you've got factors that have more than one term in it, those are the red ones. All right, if you got a factor that's just a single term, or a numerator or denominator that's just a single term, that would be a green one here, as you can see. Okay, there we go. And so you can see you got a green and a red right here. And then we learned about how to cancel with those different factors. Well, in this particular problem here, both the top and the bottom here are prime polynomials. And when you have a prime polynomial, that's just a single red one. So we have a red one over a red one right here. Okay, we can put this off to the side here. And please put this off to the side because we're going to need room for the rest of the problem here. Since we're going to end up not having to put this in lowest terms, as I'll show you here in a minute, I want to leave some room for the rest of the stuff. Those are prime polynomials, and as we learned back in that prerequisite review, you can't cancel red ones unless they are exactly the same, or if they have that same term opposite sign scenario, okay, which we saw as well. But that's certainly not the case here, and you're not allowed to cancel part of a red factor, all right? So you can't cancel the x's and just leave the 5 and the 3 there. All right, so a little review of that real quick, but make sure that you review that if needed here, because this first step, if it's not in lowest terms, if you don't get it in lowest terms when it needs to be put in lowest terms, it's going to ruin the whole rest of the problem, okay? So make sure that you remember how to do that. But this step here, step 1 does not need to be done. So I checked it, and it doesn't need to be done, okay, because it's already in lowest terms. So then that brings us to the second step, which is what? It says in the second step right here, it says find and graph the asymptotes, and it says see previous page. All right, that's back. My pages were set up a little bit differently when I wrote that originally. What it should say is it should say C above, okay? C above, okay? And why I say C above is because if you look above here, it talks about all three different types of asymptotes that we're going to have in these problems. Now, the typical rational function that we see in this section will almost always have a vertical asymptote, okay? So we're going to be looking for this on every single problem, no doubt about it. Okay, I'll show you when it doesn't. It's a very rare case. But right now, let's just assume that they all do, and then I'll talk about when it doesn't, okay? Horizontal and oblique asymptotes, all right? Every single problem either has one or the other of those two things, okay? And you'll see why here when I go through these directions. It's going to be one or the other of these two things. So you're either going to have a horizontal asymptote or an oblique asymptote, okay? And it'll be just one of either one, okay? You'll either have one horizontal asymptote or you'll have one oblique asymptote, all right? There could be some really, really rare problems where you have more than one of either one of these things, but don't worry about that here, okay? But with vertical asymptotes, you could have more than one, and you will on some problems, okay? So let's look for those now, okay? How do we find the vertical asymptotes? It says find the value of x that makes the denominator equal to 0, but, and this is why we did the lowest term step first, okay? This does not necessarily, there we go. This doesn't accurately find the vertical asymptotes unless the fraction is first in lowest term. So, see, here's the thing, you guys. Sometimes when you put a fraction in lowest terms, the denominator changes. So if you take the original denominator and set it equal to 0 and figure out what makes the denominator equal to 0 in the original one, that's not going to be the same as it would be after you put it in lowest terms and the denominator's changed, okay? And so you need to make sure to put it in lowest terms first. We already checked that, but I'm just reminding you for future problems. Then you set your denominator equal to 0, and that's how you find your vertical asymptote. Okay, so let's do that. Step 2. Vertical asymptote. How do you do that? You set your denominator equal to 0. And that's just a simple little linear equation, right? So we move the 3 over to the other side. And that right there is your vertical asymptote right there. That's your vertical asymptote. All right. So I got step 1. But we still got to do the other asymptotes here. Now remember, okay, it says that it's going to be one or the other, right? Okay, here's how you know. It says if the numerator has a lower degree than the denominator, then the x-axis is an asymptote. Okay, let's back up here. Is that the case here? Notice that this is a degree 1 polynomial up here, okay? Because it's got you got a degree 1 term and a degree 0 term. All right, so the degree of the entire polynomial, as always, is equal to the highest degree of any of the terms in that polynomial. All right, so this is a degree 1 polynomial. For the same reason, this also down here would be a degree 1 polynomial. Okay, so that is what they said right here, where it says a lower degree. That's not the case here. Okay, it's actually the same degree. So let's keep reading this paragraph. It says, on the other hand, if the numerator and denominator have what? The same degree. Now that's what, now we're talking here. That's the one that we're looking for here. All right. Then the horizontal asymptote can be found by dividing the leading coefficients. Okay. The leading coefficients, remember, are the coefficients of the highest degree terms. Okay. The highest degree terms in both the top and the bottom of your fraction are 1x and 1x. And so therefore, you don't have to write that down. But therefore, the horizontal asymptote is found by taking, and you got to say why, because remember, and let me just back up here for just a moment before I write this down. Okay, vertical lines, which is what the vertical asymptote is going to be, that's always x equal to something. We learned this back in chapter 2 when we were talking about graphing lines. Vertical asymptotes are always x equal to something. Horizontal asymptotes are always y equal to something because horizontal lines are when y is equal to some constant number. All right. In section 2.5, we learned about equations of horizontal and vertical lines. So you could review that if you like, but that's how it works, okay? Horizontal, you got the y equal to something. Vertical, you got x equal to something. Okay, neither one of these are going to have both variables in it, both x and y, all right? But again, that was from section 2.5. So what you do is you take these leading coefficients and you divide them, the top one by the bottom one, and of course that's equal to 1, right? And so that is your horizontal asymptote. Okay, so we are going to do this, and I'm not going to do it yet because I might have to change the scale of my graph, but eventually I'm going to draw a vertical line at x equal to -3, and I'm going to draw a horizontal line at y equal to 1, and that's going to be my asymptotes. If you're not sure what an asymptote is, you don't remember, or maybe you haven't heard that before, don't worry. I will explain that carefully. But that is actually going to be a key part to this graph. Okay, it's not actually a part of the graph in the sense that that's not where the solutions to the function are, but it's going to help us draw the graph. That's what asymptotes do. Okay, but we'll get to all that. All right, we're just on step 2 right now. So let's go on into step 3. This is definitely something that we're familiar with. Finding the x and y intercepts. You guys know from previous discussions that when you, again back in chapter 2 when we were graphing lines, we know that finding the x-intercepts means to make y equal to 0, and to find the y-intercepts, it means to make x equal to 0. So let's try that. For the x-intercept, I get what here? Let's see. X-intercept, I get... I need to set y equal to 0, which is the same thing as f of x. And so I make the f of x equal to 0, and I solve this equation. All right? But I can make it, remember, when you have a fraction on each side of your equal sign, all right, and I can make the 0 into a fraction like you see there, all right, then you can cross multiply, can't you? But if I cross multiply, I get 0 times something is equal to 0. Let me write that down. Okay. And then 1 times x minus 5 is x minus 5. And then you solve that equation. Move the 5 over to the other side, and that right there is your x-intercept. Okay. All right. How about your y-intercept? Again, we're still in step 3 right here. Y-intercept. Y-intercept is when you have what? It's when you have x equal to 0. So I plug in x equal to 0. And the f of x is the same thing as y. You can call it f of x still if you want. Well, actually, it's going to be f of 0 because we're going to replace the x with the 0, aren't we? Okay, but the important thing is you plug in 0 on the other side of the equal sign like you normally would with a function. And remember, when you have to figure out what a fraction is equal to, you got to figure out what the top and bottom are equal to, and then put it in lowest terms if possible. Wouldn't that be equal to negative 5/3 here? Right? Negative 5/3. Okay. And so that's your y-intercept. Okay, we're getting there. We're slowly but surely getting closer here to where we can actually graph this thing. All right, now, that was step 3. What's step 4? Okay, it says, and let me just stop for just a moment before I introduce. Actually, I'll say this while I'm looking at the directions here. What I'm about to say. It says determine where the graph will intersect the horizontal or oblique asymptote. In this problem, it's horizontal. Okay, like I said, remember it's one or the other. Okay, the only time you're going to have an oblique asymptote, and we'll see this later when we get to those problems. The only time you're going to have an oblique is when the degree of the top polynomial is bigger than the degree on the bottom. Okay? But that didn't happen here. So I just wanted to clear that up in case you were wondering about why I didn't talk about oblique. Okay? It's because we had it horizontal, and if you have a horizontal, you're not going to have an oblique. Okay? So anyway. Because we don't have an oblique, I'm just focused on horizontal right here. It wants to know when the graph will intersect it. I want to make this clear, though. There is no way that the graph can intersect the vertical asymptote. Okay, because that's where the denominator is equal to 0, and you can't have a solution where the denominator is equal to 0. Okay, so you don't need to do that. Okay, so you can make a note here. Graph will not intersect the vertical asymptote. Will not. So you don't need to check that. We're just looking at either the horizontal or oblique asymptote here. In this case, in this particular problem, horizontal. Graph will not intersect the vertical asymptote. Okay. Now, how do you figure that out? Well, whenever a graph intersects, let's first of all actually look at what the vertical, or pardon me, the horizontal asymptote is. The horizontal asymptote is y equal to 1, right? So wouldn't it make sense that we would plug y equal to 1 into our function and solve that equation? And that'll tell us where the graph meets the y equal to 1 asymptote. Okay, so I'm going to do that. So I'm going to plug in y equal to 1. Okay, I got that from here because that's a horizontal asymptote. And I get what here? Remember, f of x and y are the same thing, so I'm just going to replace the f of x with 1 there. All right, and I get this. Once again, we have a situation where we can solve this equation by making this side of the equal sign into a fraction. Okay, 1 over 1, and then cross multiply because both sides are just fractions. Yeah, both sides are just fractions, nothing else other than those fractions. If I cross multiply, I'm just multiplying by 1s, right? So I just get this right here. But something interesting happens, something we've seen before though. Okay, we get a situation where if I move the x's to the same side, they both cancel, don't they? And we get an equation where there is no variable, and this is a false statement. What did we say about that, you guys? When we have no variable in an equation, and it's a false statement, 3 is not equal to -5. The answer then would be no solution. But what does that mean as far as what we're trying to figure out here? It means that the graph, okay, thus, graph does not cross the horizontal asymptote. It does not cross it because if it did, there would have been a solution there. All right.
Welcome back. This is Mr. Wakefield looking at section 7.5.
Okay, so now we are ready to move on to step 5 here. All right. Let's take a look at that. We need to make a number line. Okay. Make it as big as you can here. We're going to have some stuff on it and a good number of things on here. Okay, what are we going to have on there? It says break the function's domain into intervals separated by the following. In other words, break the entire number line into these, break it up according to these 3 things. Okay, so X-Intercepts. What are my X-Intercepts in this problem? They are x equal to 5. So that's going to be one of the things you put on the graph. All right, let me write that down up here, even though this is just the first problem. X equal to 5. What are the vertical asymptotes in this problem? It was x equal to -3. Okay, so we got 5, we got -3, and then the x values where the graph intersect the horizontal asymptote. Well, there wasn't any, right? So we don't have to do this step this time because there wasn't any. So we break up our number line according to these 2 numbers here, 5 and -3. Let's do that right now. Always put the smaller number on the left-hand side of where the bigger number is, like that. And then what you do at this point, you guys, is you plug in numbers that are in these intervals here, okay? Just make sure that they're numbers that are in the domain, and they should be normally, as long as it doesn't make the denominator equal to 0, okay? In the original function there. And so any number you want. So like from negative infinity all the way to -3, plug in any number you want. And I just want to figure out some additional points on the graph here. It's going to help us, okay, as you'll see coming up. So any point you want, I'll go ahead and do -4. So if I plugged in -4, again, we're plugging it into x here. This number line is like the x-axis right here. You're focusing on x's here. All right. But you need to plug it into the function. So if I plug -4 into here, I would get -4 minus 5, right? Which is -9 over -4 plus 3. All right. I'll go and write that down here, at least for the first time. -4 minus 5 divided by -4 plus 3. Again, with fractions, figure out what the top and bottom are equal to. And then after you've done that, put it in lowest terms if you can. This is -9 over -1, which is equal to 9, isn't it? Okay. I'll get into all that here in just a moment about what to do with that. But again, you could plug in any number you want in between -3 and 5. You could plug in any number you want in between 5 and infinity, any number. Now, the good news with that is that I could pick 0 here, but I've already figured out what f of 0 is, okay? When I did the y-intercept, I plugged in x equal to 0. So that'll save you some time right there, all right? I can actually plug that back in again. 0 minus 5 over 0 plus... I don't even know why I'm writing this down. We already know the answer, but I've already done it, so I'll go ahead and just keep it. But we already knew it was -5/3, didn't we? All right. But you just need to have one number in between or inside of each interval here. Now let's pick a number between 5 and infinity. Okay, I'll go ahead and do 6. You could do 7 or 8 if you want. All right, any number you want. So we get what here? We get 6 minus 5 on the top, and 6 plus 3 on the bottom. That is going to be equal to 1/9. 1/9. Okay. Finally, you guys, after all of that, we can now what here? We can go ahead and start graphing this thing. Now let's take a look at our numbers here. All right, there's one number that's kind of big that goes a little bit off the graph here, and that's this 9 right here. All these other numbers that we found for x's and y's and all that, all of them should fit within this graph here. So because there's just one number that does that, and since it's not like it's 73 or some big number like that, because of that, I'm going to just kind of stretch things out here a little bit. It's okay if it runs into your words up here, that's fine. But here's 6, 7, 8, and 9 right there, and I'll just stretch the graph out here a little bit here so we can fit that in there without having to change the rest of the scaling on the graph here, okay? So let's go ahead and what is the next step here? It says finish the graph. Finish the graph by sketching how the graph approaches the asymptotes. Okay, well, that seems like it's pretty vague. So let's give more detail on that, all right? It says more details on step 6 above. How do you finish the graph of a rational function? Okay, number 1, make sure you've plotted all the points and asymptotes from steps 1 through 5. Okay, let's do that first. Let's plot all the points that we found and all the asymptotes too. All right, so start out with the asymptotes here since that's the first thing we did. X equal to -3 is right here. And when you do asymptotes, you guys, it needs to be dotted lines because they are not officially a part of the graph. Okay. As you'll see here coming up, it's not actually a part of the shape that you're going to draw for the graph. But it's going to help you draw the shape. So make it a dotted line. Same thing with the horizontal asymptote. Make it a dotted line. Horizontal asymptote at y equal to 1. So it's going to be a horizontal line that goes through y equal to 1. You can see y equal to 1 right there on the y-axis that I just cut right through there. All right, just like I cut through x equal to -3 on the x-axis right there for the vertical asymptote. So there's your two asymptotes in this problem. What are some of the points I plugged that I plotted here? I've got X-Intercept is... yeah, that's correct. 5. I just want to make sure I counted that right. Yeah, that's x equal to 5 right there. What else did I get? I got y equal to -5/3. If you put that in your calculator, that would be... I'm sorry, I fell off the screen there. There's x equal to 5. Let me back up. You see that now? So That's x equal to 5 right there. Now the next one is going to be y equal to negative 5/3. If you put down your calculator, that would be a negative 1.7 approximately. So again, just put it between -1 and -2, and that'll be fine. Okay, that's close enough right there. Okay, what else did we get? We didn't get anything for the horizontal asymptote, but we did get these 3 additional points right here. Let me plot these 3 additional points. -4, 9, where is that? That is way, way, way up here. That's why I stretched out the graph a little bit right there. Okay, in fact, I'm going to need to stretch out my vertical asymptote here as well. You'll see why here in a second. Okay, why I need to do that. What else? 0, negative 5/3. I already did that one just a moment ago. And then 6, 1/9. Here's 6 right here. 1/9 is 1 divided by 9 is 0 point something. Okay, so again, if you want to know what a fraction is equal to, you can put in your calculator. It's 0 point something, so it's going to be between 0 and 1 as far as the y coordinate is concerned, so it's about right there. Okay, and again, let me stretch out my horizontal asymptote as well. Okay, again, you'll see why this is so important. You don't always have to stretch it out way far like this, but it just helps in this particular problem, as you'll see. Okay, what do we do after we plot all of our asymptotes and all of our points as well that we found in steps 1 through 5? It says first, out of all the points you plotted, okay, how many total points do I have? I've got 3 points here, right? Okay, actually 4. Excuse me. This is a little one right here. We don't want to miss that. Let me make that bigger. Okay, out of those 4 points that we plotted there, it says take the point furthest to the left. Okay, and have the graph go from that point towards the horizontal asymptote on the left. So the point that's furthest to the left, have it go to the left. But by definition, you guys, a horizontal asymptote is something that, like any asymptote, it is something that the graph gets closer and closer to as it goes forever in that direction. So you take the point furthest to the left and you have it get closer and closer like this, closer and closer to the horizontal asymptote without touching it. Doesn't mean it doesn't sometimes touch it, but we already found out in step 4 that it never does. So have it get closer and closer to the horizontal asymptote without touching it there. So you see how my arrow is indicating that it's kind of going right along that line, but it's and if you do that, I will assume that you are doing it correctly, and you're not trying to state that it's going to touch it. All right, just as long as you get it close like that, you're good enough. But it is not supposed to touch it in this problem. But that's what asymptotes are, you guys. They are these dotted lines that the graph gets closer and closer to as it goes out forever to the left and also forever to the right. And so that's why I need to take a look at the next set of directions here. It says do the same thing with the point furthest to the right. Make sure that you, I'll get to that in a minute, but take the same thing with the point furthest on the right. Have it go from that point and have it go forever to the right. Okay, getting closer and closer to the horizontal asymptote without what? Without touching it, right? Okay, and again, the arrow makes it look like that, doesn't it? It makes it look like it's not touching the horizontal asymptote, but it's getting closer and closer to it, and it's just kind of staying alongside of it there. All right, and that's exactly what it's supposed to do. All right, so the point furthest to the left, have it go forever to the left from that point, getting closer and closer to the horizontal asymptote over there, and then the point furthest to the right, have it go towards the horizontal asymptote, getting closer and closer to it without touching it as it goes out that way. Okay. All right, what's the next set of directions there? We're almost there. For each vertical asymptote, there's only one in this problem. Take the points closest to the asymptote on each side and have the graph go from each of these 2 points towards the vertical asymptote. It will either go forever upward or forever downward. We'll talk about how you know which one of those it's going to be. Okay, so there's 2 points right here. These 2 right here. These are the 2 points out of the 4 points I plotted originally, all right, in the problem that are closest to the vertical asymptote. All right, so what you do is you take this one and you have it get closer and closer to the vertical asymptote from the left side of it going towards the right, and then this one you have it get closer and closer to the vertical asymptote as it's going from this point towards it this way. Okay, but here's the question though: how do I know that this point doesn't go up like this? Okay, it could either go like this right here, or it could go down. But it does get closer and closer to it. We just don't know which way it does yet. Okay, does it go up or does it go down? Okay, here's how I know that it goes down. It goes down because if it went up, it would have to hit not only would it have to hit the x-axis, which would be a contradiction to the fact that x equal to 5 over here is the only x-intercept. Okay, and there's not an x-intercept over here. Okay, the only x-intercept's over there. So that would be a contradiction. There's also another contradiction in the fact that it's not supposed to hit the horizontal asymptote anywhere, including right here. If it were to go up like this, okay, it would have to hit that. All right, this is supposed to be a continuous graph. You can't just jump over something because you don't want to hit it. All right, the only time that there's a break in the graph is right at the vertical asymptote itself. All right, as I'll kind of talk about that more here at the end. But you can't just jump over the x-axis and the horizontal asymptote because you don't want to hit it. So the only choice that we have is for this thing to go like this. See how it's getting closer and closer to the vertical asymptote without touching it? All right, and that arrow is indicating just that. So if you have an arrow like that, then I'll understand that you're trying to tell me that, hey, it's getting closer to the vertical asymptote, but it's not actually touching it there. Okay, all right, now, how about up here? Same thing, all right? You take the point that's closest to the vertical asymptote on this side of the vertical asymptote over here, and you get it closer and closer to the vertical asymptote without touching it over there. Again, how do I know that it doesn't turn back around and come down this way? It's because, again, it would have to hit one of these two things if it did. And we already know that it doesn't hit the horizontal asymptote. We already know that the only time it hits the x-axis is way over here at 5, and so it must go up. It can't go down and hit those. Okay? Not this time. All right, we're almost there, all right? What's the last step here? It says connect other points as necessary so that you'll end up with a graph that's smooth and continuous. Smooth meaning that there's no like sharp turns like that or something like that, that it runs nice and smooth, and then it's continuous. It doesn't jump at all except for when? Except for at the vertical asymptotes. See how it jumps from way up here to way down here? As your pencil moves from left to right, if you draw the graph from left to right, not including the asymptotes, but I'm just drawing the graph from left to right, the only time it should jump is at the vertical asymptote. Okay? The graph will never hit the vertical asymptote, so it has to jump somewhere, all right? As it moves from left to right, it has to get through there somehow, but that's the only time that it doesn't, that there's a jump in the graph, is at the vertical asymptote. Okay? So it jumps from here to here, and then this should then, since the vertical asymptote is the only time that it jumps, it should then go continuously all the way through here. So what this last step up here is telling me to do is to then connect this so that it will be continuous. Just connect the points I have left over, all right, and I'm going to do that right now. Okay? And so that is basically how you do the that last part of the graph there. Don't forget, you've got to have arrows when it gets closer and closer to the vertical asymptote, and you've got to have arrows when it gets closer and closer to the horizontal asymptote. I mentioned that actually in the last sentence of the second and third step right here. Okay, and it says there arrows and then arrows here. All right, so do that. Yes, there's a lot of stuff that we just did on that problem right there. That was just problem number 1. Okay, but now that we've gotten a lot of that explanation out of the way here, we just do the same things now on these next set of problems here. Okay, and it's going to get easier each time, as it typically should. All right, so let's keep going here. Problem number 2. Okay. Okay, the first thing we want to do is, again, check to see if the function, the fraction that it's equal to, is that in lowest terms? Let's find out. 2x plus 1, that is a prime polynomial. No GCF, no, can't factor what's left over because you got two terms and you got x to the first power. So you can't do that a squared minus b squared thing, for example, okay, on that. How about down here? This looks like something that might factor, and as it turns out it does. You can use the Berry method there. That would be x plus 4 and x plus 2. All right. Again, please review your factoring back in the prerequisite packet if you need to. All right, I'd hate to see that slow you down here. But based on my factors here, can I cancel anything there? No, I cannot. And so, but again, if something does cancel, you got to do that in the first step, or as I've implied earlier, that could ruin the whole problem, and it will. All right, but nothing cancels, so we're good. Now, in step 2, and I'm glad we factored that now on the bottom because that's going to help us do step 2 here. Step 2 says for the vertical asymptote, you got to figure out when the denominator is equal to 0. And because that is a degree 2 polynomial that you're setting equal to 0, that becomes a quadratic equation. And we need to factor that. Okay, it doesn't mean that's the only way to solve a quadratic equation, but that's usually the most popular method, and it will work here. Because if we set this thing equal to 0 and then we factor this thing, which we already have, x plus 4 and x plus 2, we know from our previous discussions that we can set those two things equal to 0 and solve those, and we get x equal to negative 4, and we get x equal to negative 2. Those are your vertical asymptotes right there. There's 2 of them this time, okay? So we're going to have a little bit more work to do this time in the final graph, but we'll get through it. All right, how do we find those horizontal asymptotes? Okay. Let's go back and talk about horizontal asymptotes again. All right. Or maybe it'll be an oblique asymptote. Let's find out. It says if the numerator has a lower degree than the denominator. Does it have a lower degree here? It does, because this is a degree 1 polynomial right here. X to the first is the highest degree. And this down here, x to the second is the highest degree. So that means that the horizontal asymptote is what? Well, according to this, it says that when it's a lower degree, okay, it is going to be what? It says then the x-axis is your asymptote. All right, so let's write that down. The horizontal asymptote is the x-axis. All right. Also known, otherwise known as y equal to 0. If you came up with the equation for the x-axis, it would be y equal to 0, because y equal to 0 is what y is equal to when you have an x-axis. Okay, just like if you had a horizontal line that went through y equal to 1, then the equation would be y equal to 1. So for the x-axis, it would be y equal to 0. I'm making a big deal out of this because the y equal to 0 is something that we're going to need here coming up. Okay. All right. So we've got our asymptotes. Step 3. What are my intercepts? Okay. For the y-intercept, we got to plug in x equal to 0, right? I did a little bit out of order from the last one, but it doesn't matter. Okay, it doesn't matter which one you find first here. The y-intercept, I've got f of 0 is what? When you plug 0 into a term of a polynomial, it makes the term disappear, doesn't it? So you get 0, 0, and 0 right here for these 3 variable terms. What is that going to leave me with here? It's going to leave me with 0 plus 1 is 1. And down here I get 0 plus 0 plus 8. 1/8. Okay, that's if you have just a normal polynomial with no parentheses. A parentheses would be different. That's why I didn't plug it into the 2 brackets here. It's easier to plug a 0 into this thing right here because you can make those x terms disappear. What's the x-intercept? The x-intercept is when the y is equal to 0. In other words, when the f of x is equal to 0. And as we found out in the last problem here, you can cross multiply to figure this out, because you could say 0 over 1, and then you can cross multiply. If I did that, wouldn't I get 0 equal to 1 times 2x plus 1? Again, I'm cross multiplying. 0 times this big thing right here is 0. 1 times 2x plus 1 is 2x plus 1. What is the x-intercept then? Well, if I move over the 1, I get negative 1. If I then divide out the 2, I get x is equal to negative 1/2. Okay. So now we know the intercepts. Step 4. When does the graph cross the horizontal asymptote? Okay. In other words, you set the fraction equal to the horizontal asymptote. Since y is equal to 0, in other words, that's why I was making a big deal out of y equal to 0 earlier. Since y is equal to 0 in the horizontal asymptote, you replace the f of x with 0. Okay. And what you'll notice here is that we just solved this equation just a moment ago, didn't we? This happens sometimes, okay? If your x-axis is the same thing as the horizontal asymptote, then the x-intercept is going to be the same thing as the answer that you'll get in step 4. All right? So, same equation, and therefore the same answer. Same equation, same answer. What is that answer? It is x equal to negative 1/2. Okay. All right, now, what is step 5? Step 5 is to make that number line. Okay, what's going to be on that number line? According to the directions, we got to put on there what? We got to put on there the x-intercept. Let me erase this and so we can do it for this problem now. What is the x-intercept in this problem? It is negative 1/2. What is the vertical asymptotes in this problem? It is negative 4 and negative 2. And then the place where it crosses the horizontal asymptote is actually the same thing as the x-intercept up there. Okay, so I don't need to write it again. All right, it's the same thing. So I have a total of 3 different things I've got to put on my number line. 3 different things. So let's go ahead and do that. Negative 4, negative 2, negative 1/2. Okay, let's see how that comes out. So let's say that I plugged in f equal to negative 5 right here. Okay, I know it's getting kind of small here, so let me zoom in there for you. There we go. F of negative 5. If I plug that into the function, I get on top, I get 2 times, let me zoom out a little bit so you can still see it. Actually, you know what? We can see it right here. It's right here. This is the function, actually, so we can just look at this. 2 times negative 5 plus 1 is what? That is negative 9 over what? Negative 9 over... And then if I plug in the negative 5 on the bottom, I get 25 plus negative 30. What is that? That is a negative 5 plus 8 is 3. And so that's going to be equal to negative 3 right here. Negative 3. Okay. All right. Let me fix that. Let me put that up above here. All right. Actually, that worked out okay. That's fine. So negative 3. Okay. What if I plug in f of negative 3 now? In between negative 4 and negative 2. What do I get on that one? I get, plugging that in, I get negative 5 on top. On the bottom, I get 9. When I square negative 3, 9. Plus negative 12 is negative 3. Plus 8 is 5. And that is equal to Wait, hold on. I made a mistake there. Excuse me. 9. Yeah, there it is. 9 plus negative 18. Excuse me. So that would be negative 9. And then negative 9 plus 8 would be negative 1. So what is negative 5 divided by negative 1, you guys? Negative 5 divided by negative 1. Okay, that would be equal to 5 right there. Okay. How about between negative 2 and negative 1? All right, well, I could plug in, negative 1/2. That would be negative 1. If I plug in negative 1, I get on top here, I get negative 2 plus 1 is negative 1. Underneath that, I get, if I square that, I get 1. 1 plus negative 6 is negative 5. Negative 5 plus 3, or plus 8. I'm sorry, I got ahead of myself there. Negative 5 plus 8 is going to be 3. And there you go right there. And then finally, this last one, since 0 is in this interval, you can just use the the y-intercept, because that's the y-intercept is when x is equal to 0. And we already found out from a previous step that f of 0 is 1/8. Okay, so those are your 4 additional points there from your number line that are going to help us graph this. Okay, finally. All right, we now need to what? We now need to follow those steps that we had from where it says more details on step 6 above, okay, to make sure we plot it correctly and graph it correctly. Plot all your points and asymptotes from steps 1 through 5. Let's just take a quick glance now. Is there any numbers here that are bigger than 5 or negative 5? Because that's how far this graph would normally stretch. No, there's not. 5 is the biggest one right here, so we should be fine as is. We don't need to like change the scale of the graph or anything like that this time. All right, so let's start plotting some points here. Or actually, we'll do the asymptotes, although it really doesn't matter what you do first. But just do all your points and asymptotes that you found. So the asymptotes are going to be negative 4. This. And negative 2. Okay. The horizontal asymptote, when your horizontal asymptote is actually the x-axis, okay, when it's one of the axes, all right, you don't need to change the x-axis into a dotted line. You could just leave it like that. Okay, just remember that it's an asymptote, okay? But when your asymptotes are not one of the x-axis or y-axis, then you got to use the dotted lines to indicate that, all right? How about the points that we found? We found what? We found that f of 0 is 1/8. 1/8 is 0 point something, so I'll put it right here in between 0 and 1. That'll be fine. What else did we find? We found that the x-intercept was negative 1/2, which is negative 0 point something. That means that it's halfway between 0 and negative 1 right there. Okay. What else did we find? We found f of negative 5 is negative 3. That means that that should be right there. Negative 5 and negative 3. Okay, what else? Negative 3 pairs up with positive 5. And so that would be right there. Okay. And as you'll see here in a minute, you don't need to know this yet, but since I already know it, I'm just going to do it right now, and then you'll see why I did it coming up here. You know, I should get this line out of here. All right. I was just trying to separate the two problems, but that's going to make it look weird. Let me get that out of the way there. I was just trying to make it easier to separate the problems, but that's actually making it harder now. There we go. All right. So it's going to kind of run into the last problem here a little bit, but we'll be all right, as you'll see here. The next one is negative 1, and then negative 1/3 is between 0 and negative 1. So that would be about here. Negative 1 for x, and then negative 1/3 for y right there. So it looks like these things are just kind of clamming up together here, all right? But that's okay. And then 0, 1/8. We already did that one. Okay. I already plotted that one. And so what I have here is a total of 5 different points. What did we learn about what to do next from the last problem? We learned that you take the point that is what? Furthest to the left, and also the point that is what? Furthest to the right. And we have both of those points go towards the horizontal asymptote. The one that's furthest to the left, you have it keep on going further to the left. The one that's furthest to the right, you have it keep on going further to the right. All right, let's start out with this one. This one, you have to, what is the horizontal asymptote? It is the, and you don't have to really do this here, but I'm just going to do it because it's easier for you to see what's going on. I'm going to extend my x-axis out and then go like this. I just want you to see clearly that it's getting closer and closer to the horizontal asymptote as it goes out towards infinity, okay, as it goes out forever. And so that's why we always put arrows when the graph goes towards the horizontal asymptote or the vertical asymptote, all right? It does that there. It gets closer and closer to the asymptote as you're going out towards negative infinity out here. How about the one that's furthest to the right here? Okay, this one is going to go out towards the horizontal asymptote. And so remember, it has to be smooth. So just might kind of make just a nice smooth little thing right here. You can have it be like kind of like a hill right here because it does eventually have to kind of get closer and closer to it and level off here. All right, don't have it just dive in here like you're diving into a swimming pool, okay? Because it has to level off in order to have that effect of getting closer and closer to the x-axis. All right, so just kind of have it go up and then just kind of get closer and closer to it. All right. All right. Now, let's see. What do we do next? We got the vertical asymptotes now, right? So now we got to do, for each vertical asymptote, take the points closest to each asymptote and have the graph go from those 2 points towards the vertical asymptote. All right. Let's start out. We got to do this for each asymptote. Let's start out with the -4 asymptote right here. These 2 points I'm pointing at right now. Those are the 2 points, one on each side, that are closest to the vertical asymptote. You got to pick 1 point on each side of each asymptote that is closest to it. And what you do is you just simply have it go from those points towards that particular asymptote. All right. Are they gonna go? Go towards the? For example, is this one going to go towards the middle and down here? Is this one going to turn around and go towards the middle? No, it's not, because it cannot cross the horizontal asymptote right there. That's why. And the other reason why is because the only x-intercept is right here. And so, since that's way over here, it cannot go towards the middle. It would have to cross the horizontal asymptote, which is also where the x-intercepts would be, okay, in this particular problem. And so, the only choice then would be for this to go upwards like this, gets closer and closer to the asymptote without touching it, and then this to go down, because it can't go towards the horizontal asymptote, all right? As we just mentioned. All right. So it's either going to go towards the horizontal asymptote or away from it. All right. Unless it's actually right on the horizontal asymptote, in which case we'll have a different way to figure that out. All right. But if the points that you're looking at are not on the horizontal asymptote, all right, then you just got to ask yourself, are they going to go towards it or are they going to go away from it? All right. And that's what's going to help you figure out what direction it goes as it goes towards the vertical asymptote. All right. How about this vertical asymptote? Well, now look at what I'm pointing at now. Again, these 2 points right here are the 2 points, one on each side, that are closest to that particular asymptote. Okay. So again, we don't want the graph to hit the horizontal asymptote anywhere other than this point over here on the right. Okay, this point right here is the only time it hits it. And so we don't want this to turn around and go towards the horizontal asymptote. We don't want this one to come down and go towards the horizontal asymptote. It needs to go away from that because it cannot hit the horizontal asymptote ever again other than way over here on the right. That's the only time. And so it must go down over here on this side. Okay. And it must go up on this side in order to keep it away from that horizontal asymptote. All right. We're almost done here. What do we do on the last step in the last problem? We'll do the same thing here. After you've done your horizontal and vertical asymptotes, make sure that they've got arrows as you approach all the different asymptotes. You should have arrows in each case here. All right. That's why we got 4 arrows for the vertical asymptotes, 2 for each asymptote. All right. And we've got 2 arrows, for the horizontal asymptote, 1 on each side. Okay. Once you've done all that, and you're down to the last step here, it says connect everything else so that you end up with a graph that's smooth and continuous. Okay, no sharp turns, it's smooth. No jumps. The graph doesn't jump anywhere except for when? Except for at the vertical asymptote, where it jumps from here to here, and then at the other asymptote, it jumps from here down to here. That's the only time it should jump. And so, therefore, this should be a nice continuous path here in order to connect the rest of the graph. So I'm just going to connect these 3 little points that are together here. All right, and now the graph is smooth and continuous as you go from the left of the graph all the way over here, all the way to the right. It's smooth and continuous except for it jumps at the vertical asymptotes. That's the only time that it's not continuous. All right. Okay, now let's take a look at number 3 here on the next page on the back side of the sheet there, or on the next page. But it's number 3. And you can see here there's some brackets here, but if you were to distribute out those brackets, it would be a polynomial on the top and the bottom, and that's why it still qualifies as a rational function. We need to do the same steps. All right. Now, the good news is that because of the brackets there, that usually means it's in factored form. And so, step 1 right here, when you have a term times a bracket, as long as the bracket is prime and you can't factor it in any further, okay, that is already in factored form. And when you have a bracket taken to a power, like we do on the bottom here, x plus 3 to the second power, it means this right here. And let me just point out what kind of factors we got here so we know whether or not something cancels. If something cancels, that means you could put it into lower terms. And like I said, that's so important here, which is why we do it in the first step. However, once again, and we'll see later when it does, but once again, you cannot put it into lower terms, so you can leave it the way it is. All right, but there will be times when it does later. But we just gonna need to keep on checking that because we never know when it's going to happen, when it will need to be in lowest terms, need to be put in lowest terms. So that's step 1. Step 2 is, once again, to find the asymptotes. The vertical asymptotes are found by setting the denominator equal to 0, but because there is because both of those brackets are the same, we're just going to have one answer here. Okay. Normally you would set both of these equal to 0, but it's going to give you the same answer, and that is x equal to -3, right? Okay. X plus 3 equal to 0 is what you would set, and then you move over the 3, you get x equal to -3. Okay. So that would be your vertical asymptote right there. What's a horizontal asymptote? The horizontal asymptote is found by, again, taking the... Actually, you know, because we have brackets, we need to clear out those parentheses just for the sake of this step. All right? Just for the sake of the horizontal asymptote, we need to clear out those brackets because we can't tell what the degree of the top and the bottom are unless we clear out the brackets. And it's the degrees that tell us what kind of horizontal or oblique asymptote that we have. All right, so let's clear out those brackets now, just for the sake of the. It doesn't mean you have to do it for the rest of the problem, but just for the sake of this step, let's see what we get here. We get on top, I get x squared minus 2x if I distribute out those brackets, or that bracket, and then down here I get what? I get x squared plus 3x plus 9. x squared, again, 4 different parts here, 4 different multiplications, x squared plus 3x plus 3x in the middle, and then plus 9. And so combining like terms there, we get x squared plus 6x plus 9. Just like the first problem that we did, you guys, the degree on the top and the bottom is the same, degree 2 and degree 2, because the highest degree terms are 2. When that happens, you take the coefficients of the highest degree terms and you divide them. It won't always be 1 divided by 1, but again, it is here like it was before. And so that means that we're going to get horizontal asymptote is equal to y equal to 1 over 1, which is equal to 1. You can just say 1 right there. Okay. And so very similar to the first problem that we did. All right, so those are your asymptotes. Step 3, intercepts. Okay, starting out with the x-intercept. Again, doesn't matter which one you do first, x or y intercept. Okay. So that means I need to set y equal to 0. When you set a fraction equal to 0, that means that the numerator, and when we do this cross-multiplying thing that we did in the previous 2 problems, you probably noticed that that's eventually what happens. When a fraction is equal to 0, ultimately the numerator is going to end up being equal to 0. And that's exactly what happens when we cross-multiply. We get this right here. Like that. Okay? So we got a term times a bracket here. All right. Don't need to distribute that out when you got a 0 over here. Okay. If I did, it would end up being a quadratic equation, you guys. And a quadratic equation is something that you factor anyway. So why not just keep it in the factored form? If you distributed out the brackets, you'd have to just go ahead and put it right back into this form again. So we don't want to be going around in circles like that. All right. So what do we get here if I set both of these factors equal to 0? I get x equal to 0, or isn't this other one here x equal to 2 if I set that equal to 0 and I solve it? Okay. I'll go and write that down here though. And so we end up with that right there. Okay, that's for the x-intercept. What about for the y-intercept there? So let's see, trying to make sure we got enough room. Oh, here we go. Let's go like this. This will be fine. Y-intercept right here. Okay. Set x equal to 0. You plug that in. Notice that the top is 0, isn't it? Because you have 0 times something. Okay. As long as the bottom is not 0, and it's not, it's equal to 3 squared. Okay, if you've got 0 divided by a non-zero number, that is automatically 0. So your y-intercept is 0. Your x-intercept is 0 and 2. Okay. So those are my intercepts. Okay. Step number 4 now. Step number 4. When does the function equal to the horizontal asymptote? In other words, plug in 1 into y, like the horizontal asymptote tells you to. Let's see how that comes out. So I plug in 1 into f of x because that's the same thing as y. And once again, I can cross multiply here, making this 1 over 1. And that gives me this right here. Okay, and then I got to solve that equation. It looks like it's a quadratic equation because if I clear out the parentheses, I get this right here. Okay, as I already found out, the denominator is equal to this right here, so no use in calculating that again. I got it from up here. The top is this right here. Okay, so same thing here on the left side. The left side is the numerator up here, so it's just the same thing. It looks like it's a quadratic equation, but if I were to move all the terms to one side, the x squareds would cancel, wouldn't they? if I move the x squared over with the other x squared. So that means that it's actually a linear equation now. The highest degree term is x to the first. So I'm going to go ahead and move over the 6x over here and then divide out since it's a linear equation, and I get x is equal to negative 9/8 because I have to divide out the 8 into the 9. Okay, negative 9/8. So that means what? The graph what? Graph crosses the horizontal asymptote at where? Where does it cross it? It crosses it at x equal to negative 9/8, which is it's between -1 and -2, because your calculator says that this is -1 point something when you put it in there. So it's going to cross a horizontal asymptote in between -1 and -2. We'll keep that in mind here. All right. Step 5. Okay. Okay, so going on to step 5, we got to make a number line here. We have to what? We have to put down all of the numbers that comprise the x-intercepts, the vertical asymptotes. Again, this is from step 5 that we looked at on the previous sheet. So we've got the x-intercepts 0 and 2, the vertical asymptotes -3, and then also the point where it hits the where it hits the horizontal asymptote. Excuse me. So we got a total of 4 numbers: 0, 2, -3, and negative 9/8. So let's put those on there. So -3, negative 9/8, okay, 0, and 2. There we go. All right. And so plugging in a number here in between -infinity and -3, I'll pick -4. It seems like a logical choice. It makes it what? It makes it -4 times -6 right here, which would be 24. Underneath that, you can plug it in either place here. They're the same fraction. -4 plus 3 is -1. We square that, we get 1. And so that's going to be equal to 24. 24 over 1. All right. How about between -3 and then this fraction is between, it's like -1 point something. So doing f of -2 will be just fine. If I plug into that, I get 8 over 1. 8 over 1. We all know how to plug things in now, so I'm going to kind of accelerate things here a little bit. Okay, so if you plug in -2 and you figure out what that fraction is equal to, you get 8 over 1, which is 8. If I plug in a number in between this fraction and 0, a logical choice there would be -1. If I do that, I get 3 over 4. 3 over 4. Okay. Let's see. I also need to plug in something in between 0 and 2. So if I plug in 1, I get, let's see, 1 is going to be, okay, -1 over 16. And then finally, if I plug in a number in between 2 and infinity, which 3 would be a logical choice for that, I get 3 over 36, which is this. If you put that in lowest terms, that would be 1/12. I don't really care if you put that in lowest terms, but it just makes it easier to see what's going on with that fraction. But when we graph it, we're just going to put it in our calculator anyway. 3 divided by 36, 1 divided by 12, no matter which one you put in there, you're going to realize that that's 0 point something. So that kind of gives you an idea of where that point is. Okay, so what I have here is I have, let's see, I've got a couple of big numbers here, 24 and 8. Remember, before we start graphing things, we want to see what kind of numbers that we have so that we can see if we need to kind of, change the scaling a little bit here. And notice that 24 is the only really excessively big number here, all right? 8 can be dealt with. We can get 8 on here just by bringing the y-axis up a little bit. So what I'm going to do, and this is no guarantee, but what I'm going to do is I'm going to, there's 8 right there. I'm going to plug in a different number besides -4 in the hopes of getting, just in this interval right here, in the hopes of getting something other than 24. Remember, you can plug in any number you want besides, as long as it goes from -infinity up to -3, you can plug in any number you want. So why not try to get something that's a little bit more manageable here? If I plug in -5, I get -5 times -7 is 35. But on the bottom, I get -5 plus 3 is -2. Squared is 4. Now that's much more manageable. That is that's a number, I'll just write down the decimal right here. That is 8.75, okay? Very close to 8 right here, all right? In fact, there's 9 right there. We can definitely get that in there. So I'm going to do that one instead of this one, all right? Just because, and again, I can't always promise that you're going to be able to find a smaller number that easily, but if you do get one that's really big and you want to try to get something smaller that'll kind of fit on your graph more easily, remember, you can plug in anything from -infinity to -3. All right, so let's start plugging in or plotting these points rather, and also the asymptotes. The asymptotes are, there's the -3 right there. Okay. And then the horizontal asymptote's at 1, at y equal to 1. So it goes through y equal to 1 there on the y-axis. Okay. Sorry, it's kind of hard to draw it sideways like that. I'm going to kind of turn my body to the side here so I can draw it more easily. That's a little bit better. Okay. All right, now. So that's the asymptotes. How about the points we found? We found the 0 and 2 are the x-intercepts right there. Okay. The y-intercept was also 0, so it's just the same point. Okay. There's not an additional point right there. It just lands on the same spot as the first x-intercept did. Okay. So that takes care of the intercepts. This point right here is where it crosses the at x. Remember, that's not y, it's x. X equal to -9/8. So since that number in your calculator is -1 point something, what you do is you go between -1 and -2. All right. And there's -1 and there's -2. So you just go in between that and put a point right on the horizontal asymptote, because that is where the graph is going to cross the horizontal asymptote. We also need to plot these other points here. -5 pairs up with 8.75, which is between 8 and 9 up here. And so let me go and put that on there. That's about right there. Okay. So it looks like I'm going to have to extend this vertical asymptote out a little bit more there. What's next here? How about -2 pairing up with 8? That's right there. Forgive me for this line going across here. That's just how the printer or the copy machine printed it out. That line is not meant to be there. Please ignore that as much as you can. It's just how the copy machine printed it out for some reason. -1 pairs up with 3/4. So that's about right here, because 3/4 is between 0 and 1. So your y value there, the function value, is between 0 and 1 here. Okay. How about 1 pairing up with -1/16? If you put that in your calculator, it is equal to -0 point something. So 1 pairs up with something that's in between 0 and 1 right here. 0 and -1, rather. You can kind of see it looks like some shape is developing here, but let's not go too fast with that. F of 3 is 1/12, which is positive 0 point something in your calculator. And so I'll put it between 0 and 1 as far as the y's are concerned there. All right, so we've got all our points that we need on our graph here, and the asymptotes too. Now what do? As we've done on the previous two problems, and I'm going to extend out my horizontal asymptote here a little bit. You take the point that's furthest to the left on the graph, which is this one, and you have it extend out towards the horizontal asymptote, okay, getting closer and closer to it without touching it. And I know it doesn't touch it over here because the only place it touches it is way over here. We found that out right here in step 4. So I'm going to go, let's get close and close to it in a nice smooth way, okay, no sharp turns or anything with your shape here. All right, just gets closer and closer to it without touching it. All right. And then the point that's furthest to the right, okay, do the same thing. You have it extend out towards the right end of the graph, though, getting closer and closer to the horizontal asymptote without touching it. All right. Like this. Put your arrows on there. Always have the arrows as it's approaching both the vertical and horizontal asymptotes. You should always have those arrows there. Okay. Then the next thing we do, like we've done in the previous 2 problems, is take the 2 points, one on each side, that are closest to the vertical asymptote. Okay, so the point that's closest on the right side of it, and the point that's closest on the left side of it. All right. Now, it cannot turn, neither one of these points can turn back around and go this way, because it would have to cross over not only the horizontal asymptote, which it can't do, because the only place it does that is over here. And also, the other reason is because it can't hit the x-axis, because the only place it hits the x-axis is at these 2 points over here. So therefore, both of these points must go upward then, because they can't cross over these things coming down, and they can't jump over them like we said earlier. So, just go like this right here. I know it's kind of hard to get close to the horizontal or the vertical asymptote on this side without going off the paper. So just get as close as you can, and I'll accept that. That's fine. All right. All right, and now once we've done that with the vertical asymptote, make sure you put arrows on both of them as they're getting closer to the vertical asymptote on both sides. And then once you've done that, then just connect the rest of the graph using the points that you still have. So it's a nice, smooth, continuous path. Okay, it should be smooth and continuous. Okay. Make this smooth here, not a sharp turn there. All right. Like that. Nice, smooth, continuous path all the way through the graph, from the left of the graph until the right of the graph. The only place it's not continuous is at the vertical asymptote. That's where it jumps. Okay. It has to jump from this side over to this side of the vertical asymptote there. And it does. Okay, so that concludes problem number 3 right there. I hope that you're starting to get the hang of this here. These next 4 problems here, we'll start to see some new things, in particular the oblique asymptote. Okay, and some additional things on the last 2 problems as well as that we haven't seen, but nothing that we don't have here in the directions already that we can't handle. Okay, but for now, I'm going to go ahead and stop this video, and then the second part of 3.5 will be in a separate video. Okay, so as usual, you guys let me know if you have any questions about these first 3 problems, and take care.